The learning objectives for this section on anchor uplift, specifically on the advanced analysis of anchor uplift, is to first understand how to refine our approximations from the basic course to realize more uplift capacity, and second, to apply more robust calculations to various bridge abutments in order to calculate a refined overburden value. Before diving into the advanced uplift analysis, we will start with a refresher on how we calculate uplift factors of safety in the basic course, BP211. Do you remember the name of our main force resisting uplift? Right. The name of the main force resisting uplift is overburden. So the basic course and outdated B2P manual calculate overburden conservatively, assuming a flat ramp wall, creating a trapezoidal value for overburden area. This is true for some designs though. So in these cases, it's not going to be conservative, right, when you have a flat ramp. But in this advanced course, we will extrapolate this area resisting overburden up and onto the slope of the ramp in order to realize some extra capacity. And like I said, this is only the case for abutments with an approach slope, of course, to be able to add that significant capacity. So here I have for you an image showing that flat ramp slope, and this is the assumption made for all bridges when you're using the basic design course. And this entire overburden area is going to have a density that we assume of 1900 kilograms per cubic meter. Now I've highlighted in this photo our extra area. So when we have a ramp slope, we can break that capital B value into a B1 or a B2, and we can use that to get a little bit of extra capacity. This triangle here is going to be our extra capacity in the increase of our overburden weight. Another conservative assumption is that the entire overburden area, except the anchor, is assumed to have the density of fill. Like I said, 1900 kilograms per cubic meter. We can find that when we split the overburden area into components and apply their specific densities, we can get a larger value overall. So I've shown in this image here using different colors, yellow, gold, and magenta and blue, that we have our fill, our concrete, and our masonry wall. All of these areas can be, all of these areas you may notice have a different or at least 1900 kilograms per cubic meter or more density value. So by that nature, when we split our components and apply these different densities, we're always going to have a larger value. Now this does make the calculations a bit more complex, and we want to make sure that we're measuring each area in CAD and being cautious as these values change with design iterations. Like I said, I found the simplest way to build this into your design tool is to measure in AutoCAD instead of trying to automate it, but you're also welcome to try and automate it. And do beware that every time you change your abutment, these values may change, sometimes very slightly, and you might notice it, not notice it, but it's best practice to have some sort of check or balance to go in and remeasure these values in CAD every time you make a significant change to your abutment.